In this video, we will look at the branch of physics that deals with the structure of the atomic nucleus and the radiation from unstable nuclei. What's interesting that the nucleus, the protons and neutrons, are about 10 times smaller than the atom itself, and they attract one another so strongly by the nuclear forces that nuclear energies are approximately 1 million times larger than typical atomic energies. So quantum theory studies this part of strong forces. When the nucleus is unstable or radioactively unstable, it can emit electromagnetic radiation, and in this case, when the radiation is emitted, we will get the gamma rays. So radioactive nuclei also emits other particles, negative and positive electrons called beta rays, and also the neutrons, and even helium nuclei or alpha particles. So when we look at the element, because not everybody in the classroom has taken chemistry or AP chemistry, or if you have taken chemistry, you may not remember this already, so we're just going to review this. So the element is going to be, the name of the element is going to be letter X. As of 2020, there were about 118 known elements in periodic table, and then there is letter A, and letter A is going to represent the mass number, which equals the number of nucleons in the nucleus, and nucleon means genetic term and used for protons and neutrons. So that's the number. In other words, it's just the number of the protons and neutrons together. And then there is atomic number Z, and this number represents the number of protons. So if A is the number of protons and neutrons, or the number of all nucleons, then the Z number, and the Z number is the number of the protons only, then if you subtract them from A, the number Z, then you get the number of the neutrons. So the search for the fundamental nature of the matter had its beginning in the speculations of early Greek philosophers, and in probably like about 2,000 years since people were trying to figure out how far we can divide the particles, or how far the objects could be divided, and what is the smallest element that we could get. So today, in our tendency toward the specialization of the different types of sciences, we would probably classify these early scientists like Dalton or Avogadro or Faraday as chemists, because they were looking at the reaction of the molecules or different materials and trying to understand how these materials work together. So one of my students in the past went to UCSD, and one of the courses that she took was advanced chemistry, and then she emailed me and she said, "Ms. German, this course is based on quantum mechanics." So chemistry and many other subjects are based, or like science subjects are based on quantum mechanics, and we looked at the applications of the bonds, but the beginning would be the quantum part, the quantum and nuclear. One of the chemists' name that you usually don't find in your books was Mendeleev, and in the rest of the world, in the United States we call it periodic table, but in the rest of the world it's called Mendeleev's periodic table. So Dmitry Mendeleev was the first one who created periodic table, and also shortly followed by the Meyer. So Dmitry Mendeleev and Lothar Meyer individually came up with their own periodic law, when the elements are arranged in order of increasing atomic mass. Certain sets of properties reoccur periodically, This led the world to the new study of the fundamental properties and individual atoms of various elements. Today, this study is specified or classified as atomic physics. When we analyze samples of many naturally occurring elements, we found that nuclides with a given atomic number can have several different mass numbers. That is, a nuclide with a Z number of protons, like Z is the atomic number. So the nuclide with Z protons can have a variety of different neutron numbers. So nuclides with the same proton number but different neutron numbers are called the isotopes. And there are different elements that have a few isotopes. So it is often convenient to refer to the sequence of nuclides with the same number N but different number Z. These are called the isotones. Once we identified a nuclide, we can then set about to measure its properties, among which can be the mass, radius, relative abundance, or stable nuclides, decay modes or half-time lives, reaction modes and cross-section, spin, and different properties. I found this information interesting and I thought that I would share this with you. So roughly 2.5 billion to 3 billion years ago, significant quantities of oxygen began entering the Earth's atmosphere. And scientists created new types of photosynthetic bacteria that produced the gas as the waste product. And the search of oxygen littered early Earth with millions of tiny nuclear reactions, blasting ancient life with radiation. As mentioned before, a nuclide is a term for an atom with specific number of protons and neutrons in its nucleus. As we will see, when nuclides of one type emit radiation, they are changed into different nuclides. So radioactive decay is spontaneous and does not require an input of energy to occur. So the stability of a particular nuclide depends on the composition of its nucleus, in including the number of the protons, the number of neutrons, and the proton to neutron ratio. During the nuclear reactions, it is that the nucleus of the atom that gains stability by undergoing a change of some kind. So some elements have no stable isotopes, which means that any atom of that element is radioactive. For some other elements, only certain isotopes are radioactive. A radioactive radioisotope is an isotope of an element that is unstable and undergoes radioactive decay. Also, what's interesting that the energies that are released in nuclear reactions are many orders of magnitude greater than the energies involved in chemical reactions. So unlike chemical reactions, nuclear reactions are not noticeably affected by changes in environmental conditions, such as temperature or pressure. For instance, carbon-12 with 6 protons and 6 neutrons is a stable nucleus, meaning that it does not spontaneously emit radioactivity. Carbon-14 has 6 protons and 8 neutrons and is unstable and naturally radioactive, which is an isotope of carbon. Among atoms with lower atomic numbers, the ideal ratio for neutrons to protons is approximately 1:1. So when the number of nuclei in the nucleus is low, we want to have the ratio 1:1 for the we wish to have 1:1 for the element to stay stable. Otherwise, it's going to be radioactive. As the number of the nuclei increases, the stable neutron-proton ratio gradually increases to about 1.5 to 1. So we want to have 1.5 times neutrons to every proton. And for the heaviest known elements, that would be the ratio we want to have for stability. For example, lead 206 is a stable nucleus and contains 124 neutrons and 82 protons, about 1.5 times more neutrons than protons. So the ratio is about like 1.51 to 1. And it is also good to note that just because a nucleus is unstable or able to undergo spontaneous radioactive decay does not mean that it will rapidly decompose. For example, uranium-238 is unstable because of its spontaneous decay over time. But if a sample of uranium-238 is allowed to sit for 1,000 years, only like thousands of the percent of the sample will have decayed. However, other unstable nuclei such as berkelium-243 will be almost completely gone, or 9.999% decayed in less than a day. In nuclear physics, they use these words as, like in radioactive decay, a parent isotope. And when they say a parent isotope is the original element, leads to the formation of the stable daughter product, also known as daughter isotope. And as time passes, the number of parent isotopes decreases and the number of daughter isotopes increases. So the parent emits an alpha particle to create a daughter. And in this case, you see in the picture that it can be alpha particle, it can be beta particle, or it can be gamma particle. Alpha particle is a positive one, and beta decay can be positive or negative, and the gamma decay, it's just the electromagnetic radiation. It doesn't have a mass. So every time the parent isotope goes through radioactive decay, you will have a daughter isotope, and some energy is going to be released, and that energy will be released in terms of alpha particle, beta particles, or gamma radiation, and sometimes you have more things involved the way the energy is released. And the alpha particles, also called alpha rays or alpha radiation, consist of 2 protons and 2 neutrons bound together into a particle identical to the helium-4 nucleus. They are generally produced in a process of alpha decay, but also may occur and be produced in other ways. So in natural radioactive decay, 3 common emissions occur. When these emissions were originally observed, scientists were unable to identify them as some already known particles, and so they named them as alpha particles, beta particles, or gamma rays. And these particles were named using the first 3 letters of Greek alphabet. So some later time, alpha particles were identified as helium-4 nuclei, beta particles were identified as electrons or positrons, and gamma rays as a form of electromagnetic radiation like X-ray, except much higher of energy of and even more dangerous to living systems. So the ability of radiation to damage molecules is analyzed in terms of what is called ionizing power. And when radiation particles interact with atoms, the interaction can cause the atom to lose electrons and thus become ionized. The greater the likelihood of that damage will occur by interacting with the ionized power of this radiation. So much of the threat from radiation is involved with the ease or difficulty of protecting oneself from the particles. And from this picture, you see that alpha particles, they're larger than beta particles, so they're easier to stop. They can be stopped by paper. Then you see that the beta radiation can be stopped by the plastic. And then so there are different types of beta radiations, right? There's positive and negative. And then it can be plastic or hand. And then the gamma radiation is very difficult to stop, and sometimes you have to put the radioactive element in lead in order to protect from the radiation escaping away from it. So the alpha particles have approximately 4 times the mass of a proton or a neutron, because there's 4 of them, and approximately 8,000 times the mass of the beta particle. And because of the large mass of this alpha particle, it is the highest ionized power and the greater ability to damage the tissue. That same large size of alpha particles, however, makes them less able to penetrate the matter. So they collide with the molecules very quickly when striking the matter, and 2 electrons will become a harmless helium atom. So alpha particles have the least penetration power and can be stopped by just a sheet of paper or even a layer of clothes. But the beta particles are much smaller than alpha particles and therefore have much less ionizing power, but their small size gives them much greater penetration power. Most of the resources say that the beta particles can be stopped by 1/4 inch of thick sheet of aluminum, and once again, it is still dangerous to be exposed to the to beta particle emission if it gets inside of you, or alpha particle emission. And gamma rays are not particles, so they don't have the mass, but a high energy from electromagnetic radiation like X-rays, or even more powerful. Gamma rays are energy that has no mass or charge, so you cannot detect them with the devices. Gamma rays have tremendous penetration power and require several inches of dense metal, like this in this picture, like lead, or to shield them. So gamma rays may pass all the way through the human body without striking anything. They are considered to have the least ionized power and the greatest penetration power. Finally, we got to the point where I can talk about different types of radiation. So iridium-168 isotope is known to go through alpha decays, and we can write the decay as, so you see there is 770 proton, the atomic number, and then there is 186 atomic mass, which is the sum of the protons and neutrons together. And so I'm talking about this problem right here. And then if the alpha particle is emitted, which has 4 protons and neutrons together and 2 protons, you see the Z number, the number of the protons at the bottom, and wherever is left is the difference of the particles that are lost. So you see that from 77, there's going to be only 75 left, because the sum of them has to give you 77. And then from 168, there is 4 went with the alpha particle, and then the rest of them stayed with the daughter isotope. And this daughter isotope is called rhenium. In the next example problem, they say that the sun radiates about 4×10⁻²⁴ joules of energy into space each second. How much mass is released as radiation each second? So if I want to calculate the mass, I can use mc² formula. Energy is given. So So I can say the energy that is released is 410 to the 26 and equals to the mass, and then I have c squared 310 to the 8th squared, so 3 squared and 10 to the 8th squared. So the mass is equal to 4.4 10 to the 9 kilograms each second. So this is how much mass is lost by the sun each second by radioactive radiation that's happening each second. And if the mass of the sun is 10 to the 30th kilogram, how long can the sun survive if the energy release continues at the present rate? So I have to calculate the number of years or number of seconds. So the number of seconds. So we have the sun is the size of 10 to the 30th. And that one I'm going to divide by how much mass is lost each second. So 4 10 to the 9th. And that will give me 4.4 10 to the 20th seconds. And if I convert this into years, there are 3.154 10 to the 7th seconds in 1 year. So this gives me answer in years, which is 144 10 to the 13 years. 13. So there are two types of beta decays, positron or electron, and it is released from a weak nucleus. So beta minus decay when an electron is emitted. So when an electron is emitted, a neutron becomes a proton, and the atomic mass is unchanged, but the atomic number decreases by 1. And when a beta plus a decay occurs, a positively charged electron or a positron is emitted, and the proton becomes a neutron, and the atomic mass is unchanged, but the atomic number decreases by 1. So here in this example, you see that this one is beta negative decay. So in beta negative decay, you're losing an electron, so that will be an electron, and the sum of them together must be equal to wherever you had before as protons. So if you add them together, that gives you positive 20. But the number of the protons and neutrons together does not change. So if you had 46 before, you still have 46 before, because you don't lose any of the protons. It's just one of the neutrons becomes a proton. Yes, that can happen. It's the quark. The quarks can change and make one change into another. And then if you have a positive decay, example of the positive decay would be something like you have oxygen, and it has 8 protons and 15 protons and neutrons together. And then you would have a positive beta decay, which is 1 beta, and you don't have any neutrons or protons coming with it. And then the result, the daughter of it, is going to be nitrogen, so it's going to be N, with 7 protons and still the same number of protons and neutrons. It's just one of the protons becomes a neutron, and the sum of both of them together should give you number 8. Also, with positive and a negative decay, you will have antineutrino in the negative decay or neutrino in the positive decay being emitted at the same time when the decay happens. So right here in this negative decay, you see that neutrino would have just like little v or lowercase v, and antineutrino would have the sign with a line on the top, so antineutrino. So here you see that energy lost as antineutrino at the same time when the decay occurs. And for the gamma decay, it happens usually after the alpha or beta decay just happened. The number A and Z, or atomic mass and atomic number, do not change and stay in the same value because the gamma decay does not carry a particle with it, just the energy of the radiation. In this case, you have still the same element, argon, and after the gamma radiation happened, the daughter element is the same element as the father element. And how they were detected or studied when the decays happen, you see here the lead box, and you have radioactive element, and then when the particles are being radioactively emitted, the alpha particles have positive charge, the beta particles have negative charge, and the gamma particles have no charge. So you can see that the beta particles will be, by using the right-hand rule, so if this is the direction of the velocity of the particles, and you use your right-hand rule, then the force acting on the alpha particle, because it is positive, is going to be to the left. So the force on the alpha particle is going to be to the left. The force on the beta particle, if it is negative, is going to be to the right. And the gamma radiation will have no disturbance when from its path when it's passing through the magnetic field. Let's solve some simple questions at the end of this video. So the three isotopes of uranium have mass numbers 234, 235, and 238. The atomic number of the uranium is 192. How many neutrons are in the nuclei of each of these isotopes? So I have the uranium with 234 and 92, uranium with 235 and 92, and uranium with 238 and 92. So if I subtract the numbers, I will find the number of the neutrons in each. The number of the protons is 92 for each of them. And I have 142 neutrons in this case, 143 neutrons in this case, and 146 neutron in this case. In the next question, they ask if an isotope of oxygen has a mass of 15, mass number 15, how many neutrons are in the nucleus of this isotope? So oxygen has atomic number is 8. That means there are 8 protons and 15 neutrons and protons together. So the number of the neutrons is going to be 7. So you would have 15 minus 8, because the oxygen has 15 and 8. I have 1 minute to finish this video. So how many neutrons are in the mercury isotope that has 200 as their nuclear number, and then 80 protons? So that would be 180 if I subtract 120 neutrons. So you have 200 and 80 for mercury, and the difference between them is 120. Number of the neutron is 120. I'm gonna stop this video at this point. There's gonna be much more practice and less theory for the next video. I just had to cover some of the basics of it. I know you watch the conceptual videos, but still I wanted to include them in my videos, not to jump into the problem solving right away. And thank you for watching, and I will see you in the next nuclear physics video, number 2. And this was number 1. Thank you.